Okay.
Hello, everyone. We are live.
Hello, everyone. I'm Aditya. I work for Interchain GmbH on the core IBC team. And the purpose of this workshop is to give you guys a tutorial on how to build your own IBC module and your own application on top of IBC. And the hope here is that you can start building IBC applications on your own without learning all the intricate details of the core protocol. So before I get started on the code, I just want to go through just the general architecture and the overview of how packets get sent over IBC and where application developers come in on the stack. So if you can see this diagram, this kind of shows how IBC packets move from chain to chain. So the way it works is that a module A that you might be writing will write an IBC packet to a particular blockchain, so blockchain A in this case. And relayers can then prove that this IBC packet was written to blockchain A on blockchain B. And once that proof is submitted to blockchain B, module B on blockchain B can then process this packet. So it's important to note that in IBC, we don't actually directly send packets from one blockchain to the other. Instead, we write it to our own blockchain and then have those proofs processed on a different blockchain to be received. Okay. And where application developers come in is that they are really on this abstraction layer of just writing their modules and working on the channel and packet level. So the way the IBC context works is that blockchains have clients, like clients of each other. And then these like clients can then create connections between these. Relayers can then create connections between these two clients. And on top of these connections, we can build channels from module to module. So here we would have an IBC channel from module A to module B. And application developers really only work with the channel abstraction. And all the connections and the clients and the proof verifications, those are all dealt by the core IBC logic, and application developers don't have to deal with that. So I'm going to move to the code, and if anyone has questions during the code walkthrough, you can feel free to ask me, and I'll answer. Cool. So you should be able to see my VS Code. If you can't, please tell me. Okay, so right now I just forked the Cosmos SDK and added my module in here. And I would recommend that if you're doing this hackathon, that you also do the same and just add your IBC application under the applications package of a Cosmos SDK fork that you own. In real life, we would probably want to write a separate standalone module, but the Cosmos SDK has tooling that makes it just easier to write the application right in here. So we'll do that for now. So the first thing I want to do is define my messages and packets that I want to be sending over IBC. So with the Cosmos SDK, the latest versions, we've transitioned to protobuf over Amino. So this is just my proto file. It's pretty simple. And the application I'm writing is I want to be able to make conversations over IBC. So in this example, I want a sender on blockchain A to be able to send a message, and then blockchain B, a user on blockchain B gets to receive that message over IBC. And then they can just converse back and forth with each other that way. So the way this would work is my module will need to write an IBC packet into blockchain A, and the relayer will then relay that packet onto blockchain B, where it'll be received and then sent to the receiver on blockchain B. So we'll see how to do that. The first thing I want to do is just define my packet data. So this is the application data that I want to be sending inside my packet. And for this application, it's really simple. I just want to send my sender address, which I'm sending as a string. So that's the sender on blockchain A, my receiver address on blockchain B, and then the message that I want to send. Okay, now that's the packet that's the application data that'll be sent inside the packet. But the message I might want to send will include additional information, like the source port and source channel. This will tell you what channel I want to be sending this packet over. So every channel in IBC is identified by a port ID, which will be placed in here, the source port, and a channel ID, which will be in the source channel. And then as you can see, it's the application data just again. And then we have timeout fields, because if I want to send an IBC packet, there might be network delays based on when the relayer sends the IBC packet. And we want to define a timeout height or a timeout timestamp so that if the packet hasn't been sent by this time, we can resend or we can do something else. So that's the message. And if you kind of want to think about it, like this packet is kind of what's inside an envelope, and the source port and source channel are kind of the address that you would put on top of an envelope to tell the relayer which mailbox to send it to. So that's great. So here you can see this packet. This is just a file that will create the new packet data. And I'm implementing the packet interface, which is validate basic. I just make sure the sender isn't empty, the receiver isn't empty, and the message isn't empty. And then I also have a message is too long error. So in my case, I've limited the message to only 100 characters. Cool. And then you can see my message.go file, which is again just a file that's for that message struct that you saw earlier. This is a constructor function, and this implements the SDK.message interface. It has a routing key, the type for implementing SDK.message, a validate basic. Here I make sure that the port ID that I sent over is valid by just calling the IBC function, port identifier validator, and again for channel. And so this will verify that the port ID and the channel ID are valid. Then again, it just does the same checks and returns. And here I have the signer of the message, and the signer of the message should be the sender of the message. So it just takes the message.sender field, turns it into an address, and returns it. Okay. That's what I wanted to show you here for now. I want to also show you the main meat of this package and what you'll be writing in any IBC application is these functions. So in order to implement an IBC module, you have to define a certain set of callbacks. So all of the callbacks that you'll ever need for to interact with IBC are defined right here. So these are channel callbacks, on-chain open init, on-chain open try. These are all the channel handshake stuff, which I'll go into. And then this is the callback that you get for on-receive packet. So upon a receipt of a packet, you can this function will be called by the IBC handler, and it can do all the application-specific logic in here. On an acknowledgement packet, I'll explain what that is later. And this is the on-timeout packet callback. So really, IBC is mostly interacting with just these callbacks. And the whole point of the rest of the module is to just implement these callbacks. So as I said before, the way the IBC logic goes is that I send a packet. That packet then gets picked up by a relayer to be relayed. The IBC logic on the receiving chain will do all of the proof verifications, all of the basic IBC checks, and in your callbacks, you just need to define what the application should do upon receiving a valid packet. Once you receive a packet, all of the core IBC logic has already been validated, so you can just focus on your application level logic. So I'll first start with how do you send a packet over IBC. So as I said, I've defined this message over here for users to send users will send this to module A in order to send a packet into the IBC module. But as you can see here, this message doesn't contain a packet itself. So I want to look at how to take this message and turn it into a packet that I then send to the IBC module. So I have this message handler right here that handles my message convo. And it takes a message convo type and just calls the keeper.sendConvo method. In here, this is where I'm going to create my packet and send it. So I just use my channel keeper to get the channel that I want, using the source port and source channel that was passed in. And this will give me the destination port and the destination channel. So in IBC, a channel will have a source port ID and a channel ID on one end, and a destination port and destination channel ID on the other end. So this is similar to the IP context, where you have an internet protocol port and an IP address on one machine, and an internet protocol port and an IP address on the other machine, and they talk over an IP connection. This is a very similar concept here, where we have a IBC port ID and an IBC channel ID on one blockchain that talks to an IBC port ID and an IBC channel ID on another blockchain, and these port ID channel ID pairs are connected by a single channel. So within this this channel keeper, I can just get the destination port and destination ID by getting the channel with my source port and my source channel, and then I can just get the counterparty information and get my port ID and channel ID from there. Also, with each channel, there's a sequence, both a sequence send on the number of the sequence for the messages that I've sent over that channel, a sequence receive for the messages that I've received over the channel, and the sequences of acknowledgements for the messages that I've acknowledged over that channel. For sending packets, I want to get the sequence send. So I just use my channel keeper again. This is my IBC channel keeper, and I can get the next sequence send using the source port and source channel, and that gives me my sequence. Now, IBC also works over object capabilities, and my module wants to exclusively talk over its own channel. So when you create a channel with the channel handshake, you'll be given a channel capability, and I'll show you that in the handshake. But that channel capability is then required for sending any packets over. So this will prevent any other modules from using your channel. So you can have your own exclusive channel by just getting this channel capability and then sending it over with the packet. So now this is just my own application logic that I've written. And in your case, you'll want to write your own application logic maybe on top of just sending a packet. So here, when I'm sending a packet, I save it into a pending message key. So this way I can know what message that I've sent that I still haven't confirmed has been received. So I get my pending message, check if there's a pending message available. It's already set. If a pending message is already set, I don't allow you to send a new message. So that's just my application logic. And if there is no pending message set, then I set a new pending message under my sender and receiver. So I'm just going to show you what is IBC boilerplate and what is your own application logic. So this is IBC boilerplate. This is something that every application module will want to do. And this is application logic. So this is something that I've chosen to do on my application, but it's not necessary for you to do, or you might choose to do something else in your application. Cool. And now I create my application-specific packet data. In my case, it's a convo packet data with, as I said, the sender, the receiver, and my message. In your custom application, it might be a different packet data. And then I just send a packet with my packet data submitted in bytes. So I have this get bytes helper function that'll just turn this packet data into a JSON marshaled bytes. I have the sequence that I got earlier, my source port, my source channel, my destination channel, and the time I hide and time on timestamp. Now this, again, as I said, you can kind of see this as the message inside your envelope that you want to send. That's your own custom application data. And all of these are kind of information that you would put on the envelope of your IBC packet so that the relayer knows how to send this correctly. And then from there, I just send my packet using the channel keeper. Cool. Then I want to show you, okay, what would happen once I receive my packet? So again, the receiving packet is very easy because IBC takes care of all of the verification logic for you and the proof verification and sequence checking. So, and the routing between different channels. So once you get this this packet into your application, you already know it's been verified by the IBC logic, it's been sent to the correct module, and all of the data inside it has been verified. So when you get this packet, you already know that this is a valid packet that has been sent by a different blockchain. So what I can do on top of the receiving packet, all I need to do is verify my custom application data, because IBC obviously doesn't know what your custom application data is. All it sees is a string of bytes for the custom application data. So I want to do my own verification on my convo packet data. And then once I verify that the data is valid, in my case, all I want to do is set my inbox message. So here I've received a message and I just set it under my destination channel and to my specific receiver with the message. Cool. Now IBC also deals with acknowledgements. So you send a message and it gets received on the other chain, but how do you know that that receive was successful? So IBC modules are allowed to write an acknowledgement upon receiving a message. And when they do this, they write the acknowledgement onto that chain, and then a relayer can then relay that acknowledgement from the receiving chain back to the original sending chain. And this will allow the sending chain to execute particular custom application logic depending on what the acknowledgement type is. So in my case, I only allow one message to be sent at a given time over a conversation. So I want to make sure that my acknowledgement was successful before I allow the next message to be sent. And if the acknowledgement was an error, then for whatever reason the receiver couldn't receive my message, then I want to clear my pending message so that I can resend the message or do something else or send something else entirely. So here I delete my pending message no matter what, but I can switch on the acknowledgement response type. So in case there's an error, all I wanted to do was delete the pending message. So now my sender is able to send a message again. But say the acknowledgement passed, then I want to set my outbox message to the last pending message that I sent. So that way I also keep track of successful messages that I sent over. So here I can just set the outbox message again with the sender, the channel, and the receiver, and my message. And then lastly, on timeout packet. So as I said before, when you send a packet itself, you're sending this timeout height, which is the height that you can time out, that the packet gets timed out on, and a timeout timestamp, which is the time that the packet gets timed out on. And if the packet doesn't get received by that height or that timestamp, then that packet is considered timed out. And I might want to do some particular application logic there as well. So again, here, all I do is delete my pending message, and this will clear the way for my sender to send the packet again. Now, this is very important to do in my application, because imagine if I didn't delete my pending message and a packet timed out, and I can't send my packet anymore, then the pending message still exists on my chain, and I can't resend anything. Because as I said in my application, you can only send a package if the pending message is clear. So here I delete my pending message, and that way I can send a packet again, even if my previous message got timed out. Cool. So these are really the meat of the application logic that I want to do. And I'll show you how that plays in the channel callbacks. So first, I'll show you just where this sent. There is no callback for sending packets because sending packets gets initiated by the module to the IBC module. So if you'll see here in my handler, I'm receiving the message. I'm receiving the message convo, and using that message convo, I am then sending a packet to the IBC module, and you'll see that happen in here. I send the packet to the IBC module. But in every other IBC use case, the IBC module is what receives the message, and then it calls a callback on the application. So you'll see here on the receive packet, the IBC message will receive a message receive packet from a relayer. It'll verify all of the IBC level logic, and then send that packet over to the application module. So this is the interface that IBC expects you to implement on receive packet. And it takes in a context and a channel types packet. So what I want to do here is, using that channel types packet, I just want to retrieve my convo packet data, my application-specific packet data. And so I unmarshal the packet data with this, this type. And if I can't unmarshal successfully, I can return an error. And I call that receive packet logic that I had shown you earlier. And I want to write an acknowledgement during my receipt. So I create an acknowledgement type. And this is just a new result acknowledgement that shows that things have gotten successful. So I just write, a dummy byte array in here, and I return the acknowledgement in the return part. So this interface takes in a context and packet, and it returns an SDK result, an acknowledgement, error. So you can see I only error in the case where I can't unmarshal the packet data. And if I can unmarshal the packet data, then I just write the message into my inbox, and I return a successful acknowledgement. Same thing with on acknowledgement data, on acknowledgement packet. All I do is I take in the IBC module expects you to implement this function, which takes in a context, a packet, and the acknowledgement bytes, and return an SDK result in error. So here I just try to unmarshal my acknowledgement bytes into this default channel types.acknowledgement struct. And if I can't do that, I error. I try to unmarshal my packet data into my specific application packet data. And if I can't do that, I error. And then I call my specific on acknowledgement packet logic that I showed you earlier. And here, these are event emitters that you can copy over. And then on timeout packet works the same way, where I unmarshal the packet data into its specific type struct, and that's copied over. I want to just clear the pending message. This clears the pending message with on timeout packet and sends out some events. Okay, so these are the functions that the IBC module expects your application module to implement for processing packets. But as I said before, your application also has control over the type of channel that it gets to create. So I'll show you the callbacks that get called during the channel handshake. So to go back to my previous example over here, in my handshake, these clients first get created, then there's a connection between the blockchain A and blockchain B, and then between module A and module B, module A and module B conduct a channel handshake. Once that is completed, then you can send and receive packets. So within the channel handshake itself, application modules can define a lot of restraints so that they only get connected to channels that they prefer. So The channel handshake in IBC is a 4-way handshake. So the first step is chan open init, and IBC will do some chan open init logic and then call the application callback on chan open init, which can return an error. If on chan open init returns an error, then the channel handshake fails, and you'd have to restart a different channel handshake so that it passes. But this gives the application an ability to choose what type of channel it gets to create. So a relayer might initiate a channel handshake with a ordered ordering, and an ordered channel type ordering would just mean that when you send message packets, they get sent synchronously, sent and received synchronously. So if I send on sequences 1, 2, and 3, they must be received on sequences 1, 2, and 3 in that order. For this application, I don't need that, and it's unnecessary restriction. So I enforce that the channel type ordering is always unordered. So here, that way, if I send on packets 1, 2, and 3, the relayer can then relay those packets in any order they choose, and it'll get relayed successfully no matter what the order is. Now I want to bind to I want to make sure that the port ID that gets sent over is the port ID that I'm bound to. So in my keys over here, I make sure that my port ID is always conversation. So just in my application, I make sure that if you're talking to my module, then your port ID has to be conversation as well. So this module only takes channels that have the conversation port ID, and that's what this is doing here. It says if the port that I have is not the port that's being sent, then I error. IBC also allows you to version your applications. So this conversation module might get upgraded, and it might be upgraded in a way that's no longer compatible. For simplicity, I make sure that my version is exactly the same as the version that's being sent over the IBC channel. So if my version is not equal to the version that I expect, which is convo-v1, then I error. And then I claim the capability. Now, this is important because this is actually an object capability key, a dynamic capability that we've implemented for IBC. And so when IBC does the channel handshake, it'll create capabilities for each channel end that the application must then claim in order to then use that channel for sending packets or receiving packets. If we don't claim the capability, then we don't claim ownership over the channel, and we can't actually send or receive anything over that channel. So it's very important that you always claim the capability. So this is something that every application module must do. And so I claim the capability under this path. And so when you're writing your application, you can pretty much just copy this. You can pretty much just copy this function as is, and just define your own version and port, variables, and everything should work correctly. Now, on-chan open try is the first message that gets sent on the counterparty handshake. So blockchain A will run on-chan open init, and then once that runs successfully, the relayer will call chan open try on the other chain, on the counterparty chain. So this is the first channel handshake message that blockchain B might execute. So again, we need to implement a callback here. And this, again, because it's the first message that we receive, we have to do all these basic checks that we did on-chain and open init on the other blockchain. So here, we make sure that the order is unordered. We make sure that our port ID is the same, is the expected port ID. We make sure our version is the expected version. And the difference here is that I also get the counterparty version. So I get the version that chan open init had committed to. So if chan open init committed to version convo v1, then I make sure that then this passes, because I make sure that the counterparty has the same version that I do. But let's say the chan open init had a different version, convo v2 or something like that, then this will fail. So this makes sure that the modules are talking on the same exact version. And again, claim capability is something that you have to do on chain open try, and you'll see it's actually passed in as part of the interface, this channel capability on both chain open init and chain open try. So you need to make sure that you claim those on both callbacks. Chain open ACK. Now this is the second message that the original handshake blockchain runs. So if I'm running a handshake from blockchain A and blockchain B, blockchain A will start chain open init, blockchain B will do chain open try, blockchain A will do chain open ACK. So here the only thing I need to check is that when blockchain B ran that chain open try method, it must commit to the same version that I had committed to. So what I do is I just check that the counterparty version is equal to my version. And again, the counterparty version here is the version that blockchain B had committed to on the chain open try message. And chain open confirm is the last message that blockchain B runs on the channel handshake. Once it gets returned, once that returns successfully, the channel has been successfully created. And here I don't really need to do any checks, so I just return nil. And what's important is that if at any point these channel opening callbacks return an error, then the channel handshake will fail, and the handshake will not return successfully. And the relay will need to restart a new handshake and make sure that all the channel handshake callbacks pass successfully. So again, this just allows channels to have control over allows modules to have control over the types of channels that they talk to. So the way I've implemented my callbacks, I make sure that any channel that connects to me has an unordered ordering, has the port ID equals to conversation, the version that's the same version that I have, and yeah, those are the checks that I make on my module. And I think for most applications that you'll be writing in this hackathon, you can just copy this over and keep these callbacks as is. On chain close init, so when I'm closing my channel, I also have the ability to call these callbacks. And if they return an error, then the closing channel handshake will fail. So here I just return an error on chain close init, and this will prevent any channel from getting closed by a user. So again, these two callbacks are pretty simple. I would recommend that you just copy them over. So IBC has a lot of certain boilerplate that you have to write in order to interact with the IBC module, and then your own custom application logic that you have to write in terms of how to write specific logic to your application state once you've received your packet. And these first 6 callbacks, they're really IBC boilerplate. And I would say for most modules that you'd be writing in the hackathon, you can just copy this over. And really the meat of your application will be in what you do inside these specific functions. What are you going to do when you receive a packet? What are you going to do when you acknowledge a packet? What are you going to do when you time out a packet? And again, you'll want to, in all of these callbacks, just make sure that you can unmarshal the packet data into your own custom application data, return an error if you can't. So these things, these initial, unmarshaling logic, you'll want to copy over and make sure that you replace the packet data with your own custom packet data. And then in your keeper, you'll want to define your own custom application logic. Cool. Now, this keeper file over here that I have just does basic, helper functions. So it sets my pending message and gets my pending message, deletes the pending message, sets inbox, gets inbox message, set outbox, get outbox message. All of these are application-specific setter and getter functions that I have. And then I also have these IBC helper functions. This helps me I call this in my chain close init callback. It just gets my capability and calls the closing init function. this will check that my port ID is actually bound. I'll tell you what that means in a bit. This binds the port. And so with all application modules, you might have a port ID and you need to bind to it before you can use that port ID. So here, my keeper has access to an IBC channel keeper, an IBC port keeper, and then a scoped capability keeper, which I'll talk about soon. But in order to bind my port, all I need to do is call bind port with my port keeper, and this will return a capability for me. And I need to, again, it's very important that I claim this capability. And when I claim this capability, that means I have ownership over this port, and I can use this port to initiate channel handshakes and do that sort of thing. So the port capability is important because I need to initiate. I need to own my port capability before I can initiate a channel with that port ID. But once I've initiated the channel, then sending packets, receiving packets, all of those rely on the channel capability, which, as you saw, we claimed during the channel handshake. Then this is just a getter and setter for my port, and a wrapper over the claim capability function that I get from my scoped capability keeper. So then I just have this genesis function, which sets my port ID in my application state. So I have, as you saw, my port ID, which should be convo. My port ID here is a conversation port ID. And if it's not already bound, then I bind to the port, and that makes my module the owner of the conversation port. So this is what I do as soon as the chain gets started up. And then once channel handshakes get started, then I'll be able to claim and bind to channels as well. Okay, then the last thing I have really is a bunch of queries. So I have the query for my pending message, a query for my inbox message, a query for my outbox message. This again uses gRPC with the latest cosmos-sdk. So I define my message request. So in this example, I'll be sending in my sender, my receiver, my channel as strings in my request struct. And given these request fields, I'll respond with the pending message that the sender has for that receiver. My inbox, again, I can ask for what is my inbox message as a receiver from the sender over this given channel. So I have all those fields here. And if I send it to my gRPC client, I'll receive my message. So this I'll send this query to say blockchain B with my receiver address and my sender address, and it'll tell me the message that the sender had sent to me, if there is an inbox message at all. And my outbox message, this is just a confirmed outbox that got sent. So once my pending message has been acknowledged, that pending message gets put into my outbox, and I can view it here using this query. Cool. Yeah. So I just want to go over a quick overview of what in here is IBC boilerplate that you'll just want to copy over for your application and what you'll want to do separately as part of your custom application logic. So when you write your own application module, you can compare to the one that I coded up real quick. And I have my code sitting up here. I have it as a pull request. That you can look at. So this is what you can look at just for how you want to change your SDK fork to add your own application module. So first, you'll want to add any messages. You'll want to add your packet data first to your proto fields. So you'll have under proto/IBC/applications / your own, hackathon application, you'll want to create a hackathon.proto file where you define your specific packet data, as I have here, and your message that you'll use to send that packet. And all that'll require will just be the fields that are inside here: sender, receiver, message, the source port and source channel, and timeout timestamp. So again, what you'll be changing is you'll be changing this packet data to have your own custom logic, and you'll be changing the fields inside here, which will again just be fields that you'll want to reconstruct your packet data. These are then queries that you can implement yourselves. And this is the RPC. I define the URL that I would have to query to get. So this is a get RPC call with this particular path, and I have these arguments: sender, receiver, and channel. Same with inbox and outbox message. I define my requests and response for each query. That's again something you would want to do. This is a CLI that I wrote really quickly. I wrote it under client/CLI. This you would copy over. This is where you would want to create. So this is my query func commands, where I create my query request using the CLI arguments and send it over my query client and print out the output. I do the same thing for inbox and outbox. And my transaction command, this is where I pass in my source port, my source channel, the receiver I want to send to, and my message. And this command will just parse all of that and create a message convo struct, and then we'll broadcast that transaction. Okay, you'll want to create a handler that will allow you to send your packet. So again, this is just a handler for your message that you defined in your proto field earlier. This part will be copied over, but this is where you'll want to do your custom logic inside your keeper function. So in my case, I set my pending message and send out my packet. You might want to do your own custom logic before you send your packet, but every IBC module will be sending a packet as part of that handler logic. My init genesis, which I went over before, will bind to the port that I have for my application. This is where I implement my query server. When I get a pending message RPC call, I just get the pending message from my keeper and put it into my response. My inbox message, I get my inbox message from my keeper and put it into my response. My outbox message, I take the request, get the corresponding outbox message using my keeper, and put it in my response. And you'll want to implement your own gRPC query server in your keeper package, as I did. So you can get inspiration from that. Your keeper, okay, so your keeper struct will always look like this. You'll need your store key for storing into your own, application store, a CDC for a codec for marshaling and unmarshaling your data, and then you'll always want a channel keeper, a port keeper, and your scoped capability keeper. This is a constructor. As I said before, these are application-specific setter and getter fields that you'll want to change. And I recommend that you keep these IBC helper functions because they're really helpful for when you create your module callbacks. So all of these below channel close init are IBC boilerplate that you'll want to keep. And then my relay code is where I do the bulk of my IBC application-specific logic. So again, I'll go through that quickly. When I send a convo, what I want to do is, grab all the information that I'll need to send my packet. So that's the destination port and destination channel. Get my channel capability so I can send my packet correctly. Check that I don't have a previous pending message already stored and that hasn't been acknowledged yet. And if my message hasn't been acknowledged yet and there's still a pending message, I return an error. So you can't send a message. If the pending message is empty, then I set my pending message, I create my application-specific convo packet data, and I send out a packet to my channel keeper. So here, that's the module creating a packet and sending it to the IBC module. Here, this will be a module receiving a packet, the IBC module receiving a packet, and then sending it to my module callback. So over here, again, I only do application-specific logic. So I just make sure that my application data is valid. I set my inbox message. On acknowledgement packet, this is when the original sender can be confirmed that the message has been received and whether it errored or was successful. If I can confirm that my message has been received, I delete my pending message right here. And if the message was successful, I also take that pending message and add it into my confirmed outbox. So here I set the outbox message to data.sender under the source channel and the receiver. And then on timeout packet, if the packet hasn't been received by a specific time period or a specific block height, then I just clear my pending message so that I can resend. Okay. And then all of these, this module.go file, you can completely copy over. And what you would want to change, are these receive these packet specific callbacks. So I would change this function to call my own, on receive packet logic, the on acknowledgement packet, and the on timeout packet, and just make sure you're unmarshalling to your specific type of packet data. Cool. So that's all of the SDK changes really that I have. This is some proto stuff. I need to register my interfaces. So I register my message convo with sdk.message. I have some errors defined, some events defined that you might want to have. I keep this expected keeper file that you'll want to copy into your types package. This is where you can just define channel keeper, client keeper, connection keeper, port keeper interfaces. This was just to prevent, too many dependencies from too many dependency circles. So when you initialize your keeper, you'll actually be passing in your IBC keepers that'll implement all these interfaces. And then I have this keys file that just defines some fields for me. So it defines my version that I had before, it defines my port ID, and then my store key and my router key, which is important for routing SDK messages. And then these are application-specific keys that I have. So I have a key for my pending message that I store all my pending messages where I store it under my sender, my source channel, and my receiver. I send my I set my key inbox message under the sender, my channel, and my receiver. My outbox under receiver, destination channel, and sender. Cool. And then this was the message struct that I showed you that you'll have to completely change, and the packet data, which is also application specific. And then all these are proto-generated fields that you can run with the cosmos-sdk proto commands, make proto-gen and make proto-swagger-gen, which will construct both your proto fields and your RPC functions. So that's all the SDK changes that I need. And I want to show you the Gaia changes that you have to make. So again, this is just a fork of Gaia that I have that I created to add my module. So the first thing I do is just import my IBC convo keeper and my IBC convo types. And what you have to do here is you add the convo keeper to your Gaia app and a scoped convo keeper. So this is a capability keeper that'll be specific for your convo module that you can then use to claim and claim any capabilities that the IBC module sends to you. So this is where that scoped keeper comes into play. I instantiate a scoped capability keeper and then use that scoped capability keeper to claim any capabilities. So I add my IBC convo types to my store keys, create my scoped convo keeper, which is just I take my capability keeper, scope to my module with the IBC convo types.module name. I create my convo keeper using the keeper constructor, and my convo module just passes in the keeper. And then I need to add my route. So I have IBC router.add route. And I want to add, so I have the transfer module already here as a route, but I also want my convo module to be added. Now, this will tell IBC how to route packets to my module. So this will register all of the callbacks that I've implemented in the IBC module so that when I receive a IBC convo packet, it'll route any of those packets to my convo module correctly. And then I just add my convo module to my module manager. And I add the IBC convo types to my module name. This will look a lot, the Gaia app.go file is really complicated, but it'll look a lot simpler when I show you just the diffs that I made. And then I just set the app.scoped keeper. So that's pretty much all I've done on the Gaia side. I'll show you the diffs that I have for that. Oh, that's unfortunate. Cool. So cool. So if you look at these diffs, these are pretty much what you'll just want to copy over, but with your own application. So you'll change all these imports to your specific application type, create your own keeper, create your own scoped keeper, add your keys, create a scoped keeper by scoping to module, constructing your keeper, constructing your module, adding it to the module manager, as I said, and creating your setting your scoped convo keeper once it's all done. So those are pretty small diffs that you have to add to a very large file. These were just to update to the latest master. And then I just had the Gaia point to my specific fork as a chain. Cool. So those are the things you'll want to change in Gaia. Now, the last thing that you would need is the relayer. And the relayer, once you set up, you can use it OVR CLK relayer. This is the Akash relayer. That's currently the one working Go relayer. So you can download this. I haven't gotten this to work yet with my application because of some configuration issues. So I will record a screen recording of this working with the relayer and show you that soon. But I can show you how the relayer works in general so that you can test it out for yourselves. Let's do /dev. So here, this is just a script to test out the relayer. It'll create a Gaia chain, and in this case, an Akash chain as well. It's creating the configurations and setting up the two chains. Then it's building my relayer and installing. It adds the chains to get to the configuration. Now it does all of the handshakes that we talked about. It first creates the clients on each chain. Then it does the connection handshake, which is connection open init, connection open try, connection open confirm. Those are things that you as an application developer don't need to worry about. Where we're concerned here is the channel handshake. So as you can see, it does channel open init, channel open try, channel open ACK, and channel open confirm. And so those are the handshakes. And now we have a working channel across a Gaia chain and a Akash chain. And this sent to transfer messages in our application, but in your applications and mine, it would send a convo packet or something else. So it's something I'll show you in a screen recording later, and I'll post it onto Discord. But all of the SDK changes and Gaia changes have already been up. They're on the pull requests, so you can look at different diffs. If you have any questions on how to build this SDK module, what you need to copy over, what you need to change, let me know. After this presentation, I'll go through this SDK repo and just point out, just as I have done in this function, everything that's IBC boilerplate and everything that's custom application logic. So when you're building your IBC module, you can start from my Convo application, copy everything over, and where IBC boilerplate is, you can leave that alone. And in all the custom application logics, you can remove what I have and add your own custom application logic. The one places where you'll have to check, there are some places where really it's the exact same thing as I have, except all you'll be doing is changing the different specific types that you're going to unmarshal to. So like in these examples, you're going to unmarshal to your own specific application data. And I'll mark that for you as well so that you can very quickly iterate on top of my example. Cool. So that's just the walkthrough of my code. Hopefully it wasn't too confusing. If you have any questions, feel free to message me on Discord. Before I hand it over, I just want to talk about the specific security concerns that you'll want to think about as a module developer and how to deal with them. So I'll go back here. So in the IBC security module, we make sure we don't enforce correctness on any specific chain. We just make sure that everything that has been committed on one chain is accurately and correctly reflected on the other chain. So if blockchain A did commit to an IBC packet, then a relayer will only be able to verify, to send that exact same packet to blockchain B, because we make sure we verify with Merkle proofs, and blockchain A commits to a very specific part in the path, and that part of the path gets verified on blockchain B. So the relayer has no ability to maliciously attack the system apart from refusing to send packets. So if you, as a module, commit to a particular packet, you can be assured that the relayer will only either be able to send that packet or just be unable to send that packet. So, in the IBC ecosystem, hopefully we have many, many relayers working for many, many different channels. So if one relayer doesn't send over your packet, any other relayer should be able to send over your packet as well. So the relayer is not something you have to worry about as an IBC application developer, but what you do need to be worried about is the counterparty module. So as a developer of module B, you don't know if module A is malicious or not. So you have to make sure that you any information that you get over that channel is somehow specified under that channel ID, so that if something were to happen where module A becomes malicious, you know that everything under that channel ID heading is malicious. So I've done that here in my application, and I'll show you with my keepers. Every time I set an inbox message or I set an outbox message, I don't just set it with the sender and receiver. I also set with the source channel. So if you look at my key, I set it under the sender, the source channel, and the receiver. And the reason for this is that now whenever I have my inboxes, I have an inbox per receiver on each channel. So if I'm the same receiver on blockchain A and blockchain B, I'll have different inboxes on each blockchain. And if a sender sends from one blockchain A, if the same sender sends from a blockchain A and blockchain B, those will come to two separate inboxes. The reason for that is because if blockchain A becomes malicious, then only blockchain A's inbox will get affected. If I had an inbox just for the entire sender, where regardless of what channel it gets sent over, it all goes to the same inbox, then if any blockchain on a specific channel becomes malicious, I won't know which message in my inbox to trust and which message in my inbox to not trust. So by separating my inbox by channel, I can make sure that if one of those channels ever become malicious, then I can know that the inbox for that particular channel is untrustworthy. But I can still trust all the messages that came from the other inboxes, from the other channels. So that kind of removes the scope of the attack if a particular module becomes malicious. And you'll see in the transfer module that we have for transferring fungible tokens, we do the exact same thing. Where in here, in our packets, our denom is actually a trace where, let me show you here. Yeah, so we have this trace where the denomination of my coin itself will tell you what port ID and channel ID it came from. And that way, we have the full coin history of where the fungible token packet has gone. So if any chain within that channel history becomes malicious, we'll be able to tell which coins to trust and which coins to not trust. So when you're building your application modules, you want to make sure that when you store things, you know which channel they came from, so that you can preserve the security of your system as well. So that's an important thing to keep in mind. The other important thing to keep in mind are the capabilities, as I mentioned before. If you want to look at the capability documents, I believe there's an architecture ADR that I can send over the Discord. But the capability module is defined right here in x/capability. And in any chain that you run with your application, you'll want to make sure that you have both a capability keeper overall and then a scoped keeper for your particular application module. And you can call that by scope to module. And as I said, in those channel handshakes, you'll want to claim your capability. You'll want to claim your port capability on Genesis. So in my application, my genesis.go binds the capability right then and there, which will claim the port capability. And then on each channel, when each channel is getting created, you will want to claim your capability there as well. And that's something that I've copied over in my module.go file. On-chain open init and on-chain open try will claim the capabilities for you. Okay, so that's I think the two things I wanted to talk about from a security perspective. The reason we have capabilities is, again, just to make sure that once a relayer creates a module, it creates a channel on behalf of your module, only you have access, only you have ownership to that module. So in the IBC security model, module A, where do I have it? So this blockchain may have many different application modules. So it might have module A and module C as well. And module A and module C will both be talking to the IBC module. They'll both be talking over their own channels. But we want to make sure that module A only talks over channels that module A owns, and module C only talks over channels that module C owns. Similarly, module A only talks over ports that module A owns, and module B only talks over ports that module B owns. And the way we enforce this, the way the IBC module enforces this, is by creating dynamic capabilities for each channel and giving them to the specific modules to then claim. And then once the module has claimed those capabilities, then they can use those channels. If you don't have the capability, then you can't use that channel. That way, module C will never have module A's channel capability, so it can't use any module A channel. Yeah, so are there any questions on either the IBC security model, how the IBC packet overlay works, or the workshop that I just talked about?
We have no questions so far.
Okay. So in that case, I will push all of these changes that I talked about. I'll make sure that you have a clear understanding of what's IBC boilerplate and what isn't. And I'll both post it on the cosmos-sdk repos and post it on Discord. And if you guys have any questions while you're building your own application modules, feel free to ask me. I'm on the hackathon Discord, and I'll respond to your questions either over Discord itself, or I'm happy to hop on a video chat and debug with you if that's necessary.
Great. Thank you so much for joining, and thank you for the workshop. We'll have a recording available on YouTube channel as soon as this workshop is done. So feel free to go there and watch the recording. You'll also find all the mentors in the Hack Item 5 Discord channel. Please go there if you have any questions, if you need anything that you need help with. Over 40 mentors are there, eager to help you, so jump in there. We'll have another IBC workshop coming in about 1 hour. And hopefully, if you have any questions, we'll also see you there. Thank you so much, Aditya, for coming to the workshop and presenting. And see everyone in Discord. Thank you so much.
Thank you.